Hello, can you hear me? Uh,
Yeah,
yeah,
Savarish, we are streaming right now.
Okay.
I don't think we are live, are we?
Hello, can you hear me? Uh,
Yeah,
yeah,
Savarish, we are streaming right now.
Okay.
We are streaming right now. We are streaming right now. Because I'm unable to see that if we are streaming or not. Okay, wait once. It says live. Okay, only the privacy thing. What are the other options that you have? In privacy, what are the other options that you have? Unlisted and okay, fine. Then change it to public once. Could you change it to public and stream again? Then it should work. All right. I'll once verify again. Stream again. Then it should work. All right. I'll once verify again. Stream again. Then it should work. Yeah. I guess everything looks fine. Yes. Hi guys. We'll be waiting for 5 more minutes since people are joining in. Today will be our 7th session, and it'll be introduction to computer vision, and we'll be also looking into some popular computer vision models like convolution neural networks and etc. So stay tuned. And also, just want to inform or make another announcement about the mini quizzes. So we haven't shared the mini quizzes of session 5 and session 6 yet. We'll be doing that by tonight or by tomorrow. And we'll also be posting today's mini quiz also pretty soon. So sorry for that delay, but by tomorrow evening, all the 3 quizzes will be out. And also do have a look at our Insta story, because we are having some more questions there as well based on whatever has been taught in the sessions. So that will also be a very good revision for you guys. Apart from that, I guess a few of you were asking about the task 2. Till now, we have only shared one task. The second task will be posted soon on the GitHub page. And as soon as we post it, we'll be informing it on all the WhatsApp groups. So you need not worry. And we'll be also giving you sufficient time to attempt those. We'll be having in total 3 tasks for this entire summer school program. The task 1 is already over. Now we'll be releasing the task 2, which will be based on implementing the ML models that you have learned so far. And we'll be having another task 3, and the details of task 3 will be shared soon. So the people who have missed more than 2 sessions, please ensure that you attempt these tasks, okay? Because this can be considered as a compensation for your attendance shortage. And also the mini quizzes, even though they are not graded or we don't consider them for attendance, they will definitely help you to get a better grasp of what has been taught in the session, and you will be able to understand things in a more better way. Like we have also framed few questions on topics which are generally misinterpreted by people, or are the topics which people generally don't have complete clarity upon. So in order to ensure that your concepts are clear and you have understood everything, you can definitely attempt those quizzes. We'll be starting at 5 p.m. So today's instructors will be Shabarish and Ryan. Okay. And also the entire content and material for today's session has been posted on the GitHub page. Have a look at that. And all the recordings of previous sessions and even today's session, once the session is over, will be uploaded on our YouTube playlist. Playlist link has already been posted in the groups. And adding to that, attendance QR will be shown during the session. Scan those QR codes to mark your attendance for today's session. And we'll be not sharing the links in WhatsApp groups for attendance, or not even on the YouTube live chat, as mentioned earlier. It is to ensure that people who are only in the session can get access to it and not the rest. And also, we have shared a Slido Q&A page link where you can post your questions. The coordinators will be taking those doubts. Okay. And always feel free to, so the Q&A page is just a medium for you to ask your doubts. We are not forcing you guys to post your doubts only on the Q&A page. If you want to speak out and get your doubt cleared immediately, then you can just raise your hands so that our instructors can view that, and they'll give you mic access so that you can unmute and speak. And that is also one of the reasons why we are having live sessions, so that we can interact with you in live and also get your doubts clarified immediately instead of keeping them for some later time. And also the attendance QR has to be scanned by all the people, not only the people who are attending the session on YouTube, but also the people who are attending the session on MS Teams. It is applicable for all. I guess those are the major things which I wanted to announce.
Oh, hi guys. I'm Sabarish. First of all, am I audible? Uh, right. So, Ryan, can you just check if I'm audible?
Yes, you are audible.
All right, guys. So, um, welcome, guys. This is Sabarish. Wait, the video is lagging. So yeah, I'm Sabarish. Today I'll be joined with Ryan. We're both coordinators of AI Club IIT Madras, and today we'll be taking up the seventh session in our summer school, Introduction to Computer Vision, and we'll be going to the most basic CNN models. So without further ado, I'll start my presentation. Okay. So before we begin the presentation, I just want all the attendees to scan this QR code. This is the Slido QR code that I'll be using to take your doubts. So you can put your doubts through this link into the Slido, and I'll be taking some breaks in between the presentation to clarify all of your doubts. And as Rutvik has already mentioned, you guys can also raise your hand in Teams. But yeah, but if you don't want to do that, you can also do it through Slido. So I'll just give you guys a minute or two to just look at this QR code and scan it. Okay, so yeah, so I think that was enough time for you guys to see the QR code. So yeah, let's get on with our session. Introduction to computer vision, and we're going to be going with the basic CNN and models. Now, before I begin, I just want to tell everyone in this session that this is going to be a completely beginner friendly session that there so there aren't going to be any prerequisites that's going to be needed from the previous session. So if you have ended up missing some of the previous sessions or weren't able to attend them or weren't able to look at the recording, that's perfectly fine. This session has been made so that everyone can understand it. So without further ado, I'll begin. So first, let's look at what is CNN. CNN stands for Convolutional Neural Network. its basic definition is that apart from our traditional neural network, which contains like entirely of nodes and multiple layers, yes, this is another class, and this class of neural networks essentially is what we're going to be is what we use in order to get very important information from images. Now, this is a simple definition, but I want you guys to focus on one thing, and that's the word convolution. Convolution is like a special mathematical operation essentially, and that is what makes this model really effective. We're going to be looking into that further on, but I just wanted you guys to know about why we're learning CNNs. All right, so in this session, we'll be looking at the following three topics. Okay, so first we'll be looking at what are grayscale or RGB images. Those are the commonly used images in computer vision. Then we will go on to the convolution operation, the simple mathematics behind it, and finally we'll go on to the machine learning part, to not the code but the theory behind the convolutional layer, that is every single part of the convolutional layers. So yeah, it contains the four things. So after this we'll be having a small break, and then my friend Ryan will actually be implementing this using PyTorch code. So yeah, so I'll be dealing with the theory. After the break, Ryan will be showing it in action in code. So do stick around for the entire thing. So yeah, let's get started. All right, now the first thing, guys, is that we take a lot of images with photos, and most of our photos just contain colors. But but I want you guys to look at the image that I have here, the 8. Let's say that I've taken an image of an 8 and I just converted into it black and white. So this is, we look at this and we say that it's an 8, and that's it, right? But the problem here in computers essentially is that we can't feed such a colored image into a computer and allow it to understand that, because computers can't process colors just like that. We need to convert it into something that computers can understand, and that's why we study the images as grayscale or RGB images. So the 8 that I have right here, this is something that's known as a grayscale image. Essentially, there has been some person who's just written this number 8, and as you can see, every single pixel in this image, it will have some varying intensity of the color white. So in these regions where there's been no white, essentially, it's completely black, and there are brighter regions where it's completely white. All right, so just a minute. Yeah, so this 8 right here is what we have as a colored image. Now, what we will be doing is that we need to convert this into a numerical matrix, right? And this numerical and we need to convert this into a numerical matrix and assign a numerical value for every single pixel in this image. And how we do that is that we take a scale like this, which is known, this is the scale, and we assign values ranging from 0 to 255, and this range of values depends upon the intensity of the color white. So if it's completely dark, it's given a value of 0, like you can see in regions here. If it's on the brighter end, it's given more larger values. And right now, guys, we've taken a very simple image and converted it into a numerical matrix, and this matrix essentially is what we can feed into a computer so that it can understand it. And so if we want a computer to learn to identify it's an 8, we have to feed it in like this. So yeah, let's go. But more in real life, however, we'll be dealing with colored images, right? The world around us is colored, so we'll be dealing with colored images. So how do you convert a color image into the same thing that I've shown before? Now, the very interesting thing about colored images is that you can take a colored image and you can split it into its three counterparts: red, green, and blue. And effectively, these three counterparts capture the entire information of the colors with. Okay, since we have done this, we have a red counterpart, we have a green counterpart, and then we have a blue counterpart. And what we can do here is that, just like in grayscale images here, where we took a scale depending on the intensity of the white color that's been going in from 0 to 255. Here we can take the intensity of each color.
Could you stop a moment? There's an issue with the YouTube stream.
Okay, so yeah, sure. Okay, so everyone on Teams, let's on hold for some time. So there's an issue with people on YouTube. All right. Yeah, I am. I came to the 6th slide. Guys on Teams, just wait for some 2 or 3. Did it change it? Did it change? Wait, so are you guys, did it go from did it change? All right, so where did it stop in YouTube? Did it stop at the 2nd slide or something, or like? I probably have to explain that again, right, for the people in YouTube.
Yeah, probably once can you go through it again? And also the people who are attending the session on YouTube, can you react or once message on the WhatsApp group so that we get to know if everything is fine?
Okay, guys. So yeah, everyone on Teams, we're just gonna do this again for everyone on YouTube. So yeah.
Yeah, I guess now it is fine. You can once revisit those topics and then you can continue, Shabarish.
Okay, fine. So yeah,
cool.
So cool. So convolutional neural net. So yeah, so in this session we're gonna be talking about convolutional neural networks. So this is another class of neural networks that we're going to be using to get important information from images. And the special part of convolutional neural networks is essentially that it's a mathematical function, a very special mathematical function that turns out to be extremely useful for image detection. So yeah, so as we saw earlier, these are the content for today's session. We're going to be seeing what are the grayscale and RGB images, the images that we usually input into the computer. We're then going to go for the convolution operation, essentially, what's the mathematical convolution operation. And after that, we're going to be looking at the layers of the CNN. So we're going to be looking at what convolution is, what are activation functions, what is pooling, etc. So yeah, so it's all quite simple. And as I said before, this is completely beginner-friendly session. So you guys don't need any prerequisites from the previous sessions. So yeah, without any further ado, we'll start, right? So yeah. Number 8, and basically when we see it, we can sense it's an 8 by the difference between the colors. So we can see it's white here, dark and black here, and all that. But we're talking about computers, and computers can't just read colors. Essentially, we have to feed it into a computer friendly format. And how we do that essentially is this is a black and white image, or a more better terminology will be this is a grayscale image where every single pixel has a different intensity of the color white. So what we do is that we take the different intensity of the color white and we put a scale of it. So a 0 essentially would be a 0 intensity of color white, which is just black. Around the middle region, you can see it going towards gray, and at the end we'll see that it's completely white. So we convert every single pixel in this image, in this original image, it's into a numerical value depending upon the intensity of white there. And by doing this, we've successfully converted a simple image into a numerical matrix, something that can be actually inputted into a computer. And this, my friends, is a grayscale image. All right, now let's go on to colored images, right? Because colored images are what we deal in most cases in real life. And how do we feed a color image into a network? So as you can see, this is an image of a dog. And the very interesting thing about colored images is that colored images can be split into red, green, and blue counterparts. Essentially, every single colored image that we have can be split into these counterparts, and then so if we combine these three, you'll get them back. So there is no information that's being lost there. And since these images are unicolor, that is, these in every single red, green, and blue image, it's just one color. Every single pixel of this image will be a varying intensity of red, and here it will be a varying intensity of green, and here it will be a varying intensity of blue, right? So we can do the exact same thing that we did for grayscale images. What we can do is that we'll take this red counterpart right here, and we'll assign a numerical value for every single pixel, like I've done here, depending upon the intensity of the color red. So if it's more intense, we'll have a greater value, and if it's less intense, we'll have a less intense, as in if it's dark, right? Because if it's dark, there is no red color there. It'll have a lesser value. So basically, instead of just getting one output from the image, we'll be getting three outputs. So we'll be getting one for the red counterpart, we'll be getting one for the green counterpart, and we'll be getting one for the blue counterpart. And just a small heads up, guys, this outputs that we're going to talk about are usually referred to as channels. All right, so I don't want you guys to be confused about it when I use it again. I will clarify that, but for now, these outputs, every single outputs are called channels. So in a grayscale image, you'll only have one channel that's being outputted from the input image, while in RGB images, you'll be having three channels. So yeah, this is how you take any image, a black and white image or a colored image, and process it so that you can make the computer understand it. Now, before we go on to CNNs, essentially, let's look at a very important question, right? Why do we even have to learn an entire new class of neural networks while we already have the traditional ones? And mainly, there are two important reasons why we should do that. You see, let's take this very simple image. This is a very simple image of 8 that we saw in the first slide, right? And if you look at the number of pixels in this matrix, so it's 16 pixels wide and 24 pixels is by length, right? So that's 16 into 24, which is almost 384 pixels. Now, if you were to be inputting this into a network by its own, what will happen is that you have to create almost 384 input nodes in the input layer of our neural network, right? And each of those input nodes will have to be connected to another node in the hidden layer, and so on, and so on and so forth. So if we take the traditional number of 36 nodes in the hidden layer, that's almost 13,824 weights and 13,824 biases that we'll have to be dealing with just two layers. And this is for a simple image, guys. So this essentially will take a huge amount to compute. And it's not favorable to actually create a neural network like that. So the solution is that we have to also decrease the amount of inputs that we are taking in from the image without losing the important features. Now, another problem is that this was an image of 8. Now, this is also an image of 8, but as you can see, this image of 8 has appeared to have slightly moved, kind of, right? So this is kind of straight, and this is kind of like wiggly. And what will happen in traditional neural networks is that the traditional neural network will not be accurate, because if you look at the previous slide, we'll be training the neural network, the input layer of the neural network, such that and such that every single input node in the input layer will be taking in its input from each pixel. So every single node is trained for every single pixel. However, that's the case for something like a regression problem or something like that, where we take parameters and find out output. But here in an image, what is more favorable essentially is it is better to find out features of an image. So if I'm looking at an 8, I know it's an 8 because there is a circular part on top and a circular part on the bottom. And making the model learn that instead of learning what each pixel does is a much more effective thing. And so see, there's a circle here and a circle there. So if you were to train the model in that fashion rather than training it traditionally, that will be better. So these are the two reasons why traditional neural networks, that is the ones that we've been talking about, are ineffective in the case of image detection. So the solution that people have come up with over the years to combat this problem is CNNs, that is convolutional neural networks. All right, the convolution operation. So now, guys, as I told you before, the convolution operation is the convolution is a special mathematical operation, and here it's simple. So we're just going to be looking at how we end up doing that, right? So yeah. Before I go to the convolution operation, I want to define something known as a kernel, because we're going to be using the kernel to do the convolution. So what a kernel is that it's basically a small matrix, like a small, or it's usually 3 by 3. So it's a small 3 by 3 matrix, and we will be using this small 3 by 3 matrix to extract the required features from the given image. Now remember that this kernel is essentially much smaller than the input image, and we'll be having different kernels for different tasks. So there'll be some kernels that do blurring, some that do sharpening, some that do edge detection. Yeah, so we'll be looking into that further. I just wanted to this is just a heads up, so don't worry about this. But basically a kernel is a small matrix, a small 3 cross 3 matrix. So let's see how we'll do convolution. All right, so guys, so let's take this small matrix. Now I want you guys to imagine that this is a small part from the image matrix. So right, so we had this image 8, right? Let's just say that I took a small subpart from this image 8, and I've just kept it here. So I've just taken a small subpart so that we can look at convolution specifically. So this is a small 5 by 5 subpart. And what convolution essentially does is that we're going to take this 5 by 5 matrix and we're going to do something called a dot product, like with the kernel. And it's nothing fancy essentially. What we're going to do is we're going to take this 3 cross 3 kernel, and we're going to be keeping it, and we're just going to layer it on top here. So as you can see, I just took this kernel and then I just put it on top of the original image matrix. So we'll be having these values. So as you can see that the larger numbers represent the numerical values from the pixel, while the smaller ones are from the kernels. And what we're going to do is that we're going to multiply each number by the number that's present in the in its square essentially. So from the image matrix we have a 3, and from the kernel we have a 0, right? So we'll be doing 3 into 0. Similarly, we have a 3 here from the image matrix, and we have a 1 here from the kernel. So we'll be doing 3 into 1. And then again, 2 and 2 from the image matrix, 2 from the kernel, 2 into 2. So as you can see, it's just a direct correspondence. We're just going to take every single image numerical value from here, and multiply it with here. And we're going to be summing up the products. So it's 3 into 0, as I said, 3 into 0 plus 3 into 1 plus 2 into 2, and so on and so forth. And when we sum up all the values of this convolution, we'll get a single numerical value, right? And that numerical value is the result of us doing a convolution over this specific part of this image. Now, how do we go on from this? So what we've done here is that we've just taken this and put it on the next 3 cross 3 is subpart. So before it was in the top leftmost corner, and now it's been slightly shifted to the right. So it's it's in the so it's now here, and we're gonna do the same thing. We're gonna be looking at this number, and we're going to be multiplying by its corresponding number in the kernel. So that's again 3 into 0 plus 2 into 1, which is here, and then 1 into 2, and so on and so forth. And again, just like we did previously, we're going to be adding up all the convolutional, all the products from the convolution operation, and we'll be getting a final value. And here it's coincidentally also 12. So we have to do this for the entire image matrix, right? Like for the entire 5 cross 5 image matrix. So this animation right here is just tells you what we're doing. So as you can see, it's putting that the gray part and every time is the kernel, and it's overlaying on every single 3 cross 3 subpart of the image matrix, and it's giving a corresponding resultant. And here, so here it's 12, then 12, then 17, then 10, then so on, and so on and so forth. So what we've done is that we've taken a small part of an image matrix, we've taken a kernel, and we have overlaid that kernel over every single subpart, every single 3 cross 3 subpart of the image matrix, and this has helped us generate a new image matrix. So this is the previous one, this is the original one, this is what we get from the image itself, and this is what we get after convolution. So yeah, so that is basically, my friends, the convolution operation. It's a simple mathematical operation, and one important thing that I want to mention to everyone is that this symbol might be confusing for you guys, is because these both look like matrices, but do not confuse this with matrix multiplication. This is a convolution. So we're gonna, so yeah, so that I just wanted to clear that. Right. So here's another example. Well, here we have another subpart of an image, and here we have another kernel. This is a different type of kernel than the one that I've used before. And as you can see, what we're doing is we're taking this number, multiplying it by this, taking this number, multiplying by this, and adding all the products together to get the final convolution value. And again, and if we go for the entire image, we'll be going from this image times this kernel will be equal to this new image. So yeah, 50 into 1, 165 into 0, and so on and so forth. So yeah, that I guess must have been yeah. So that, my friend, is the convolution operation. Yeah. So that's so moving on. So why exactly do we do convolution for image detection, right? So there are many different types of so there are many different types of mathematical operations. So why are we doing convolution specifically? And so that's what we're going to be talking about now. You see, when we're convolving a specific image matrix like the one that we saw here with the kernel, what we're doing is that we want to extract the information from every single pixel. So this is basically a small part, and these are all pixels that we convert to numerical values. So we want to get the information from every single pixel, and what we do is that, let's say that, so the first operation, what it actually does is we want to get the information that's been stored in this pixel, which has the value of 0. But the thing is, as I talked about earlier, in the traditional neural networks, we can't just extract the information of each pixel individually, because if we do that individually, we'll not be extracting the features. We'll just be extracting individual pixel information, and that will not work. What we want to do essentially is extract the information from every pixel along with the influence that its neighboring pixels will have. So doing this essentially allows us to extract the features of the image. So yeah, so when we're putting this kernel right here, what we're doing is a simple mathematical operation, but intuitively what it's doing for the image is that it's taking the information of this pixel along with the influence that its neighbors might have. So to explain, to just see that in a better fashion, I want you guys to look at this. So this, let's say that this, what we had here was a grayscale image. So this is a very random part of a grayscale image, and there are, you guys can see some specific regions, right? So if you could see this region is like a particularly a dark region where the intensity is mostly zero, and in this region it's mostly bright. So we can assume that the image is going from a darker region to a brighter region. And by convolving it with the matrix, with the kernel that we had earlier, we'll get this new result. We'll get this 12, 12, 16, and so on, 3 cross 3 matrix. And let's look at that thing. As you can see, it is effectively gotten not the individual pixel information, but the features of the image. So if there was a dark region right here, we captured it here. And here there is a region, as you can see, it's going from dark to light. So it's going through black, gray, white. And as you can see, and here, look at it. It's going from black, gray, and white. So we have been able to successfully capture the features of the image by doing this convolution. So we've taken so we've taken this 5 cross 5 image matrix, and we've successfully been able to output this, and this output from the convolution was able to get our get the features from the image. Right. So before we go further, I'll just put up a poll for you guys. This just a small refresher question. So just hold on for 2 minutes. Yeah. So I think you guys can see my screen, right? You guys can you guys see the Slido screen? Ryan, can you just confirm if you can see the Slido screen?
Yes, it's visible.
All right, so guys, I'm just gonna give you guys some 2 minutes to just scan the QR. It's just a small question which is going to be refreshing what we've just looked into for the past 20 minutes. Okay, so I believe that was enough time to. Okay, I'll wait for one moment. I'll wait for one more minute for everyone on Teams and YouTube to scan the QR. All right, guys. So I guess that should be enough time. Right, that should be enough time. Right? Yeah. So let's go to the first question of this session. So come on. So yeah, let's look at. So this is the first question. Wait. Why are there? Wait. What are you closed? Oh, sorry. I believe it should be active now. Are you guys able to vote? Yeah, sorry, I accidentally locked the poll. Sorry, but yeah, it should be open now. Yeah, so you guys can still see the QR. So yeah, you can still join in. We'll be giving 1 minute for everyone to attempt the questions. Okay. Okay, so I'm just gonna be waiting for some more seconds. So yeah, all right, everyone. I believe that should be enough time for uh, the poll. So I'll be locking the voting right now. And yeah, let's see what the correct answer is. So yeah, a majority of you guys did get the correct answer. It was unable to process translation of image. But let's look at what the others have thought. So yeah, this was actually a trick question. As I said before, ANN, which is a normal neural network, will take more time to do, not less time. So this was a trick question. And for those who thought that it was unable to process image data, that's also not truth. As I told before, we'll be converting every single pixel into a corresponding numerical value, right? So we can input the numerical values. The problem is it will take much more time to compute, and also as people have responded, it will not be able to process the translation of the image. So yeah, I hope that that's clear for you guys. So let me just deactivate poll, and yeah, so yeah, I believe that should have been a good refresher for the ANN part. Now let's get back to the presentation. So we've looked at what a convolution is, right? Before we go on to the later layers of the CNN, I want to talk about a very important difference, and that is filters versus kernels. You see, what I used in the previous operation was I called it a kernel, and the kernel and usually in the computer vision usually in computer vision the terms kernel and filter, they're used interchangeably. But however, there is a very slight difference between them. You see, filters are essentially groups of kernels, and they are used in convolving the RGB images, which have 3 channels. So to put that in simpler words, if you remember, with RGB images, which are essentially colored images, they will be having 3 counterparts, right? Well, they'll be having one red counterpart, one green counterpart, and one blue counterpart. So 3 different like images, and we have to do convolution on every single one of them. So we can't just have one kernel. We need to have 3 kernels. So those groups of 3 kernels is what a filter is. So this filter terminology is something that we essentially use only when we are talking about RGB image. Now, important thing is that in each filter, the kernels might be same or different according to the features that we need to extract. So here, as you can see in this animation, we are getting an out. We're using a kernel. This is basically a kernel, and we're getting outputs. So this can be the same kernel, like you saw here. This can be just one kernel. This could be just one kernel. Like let's say we're using this kernel, we could just use all of this over the red, green, and blue counterparts, or we can use different kernels. So yeah, so that's an important difference that I want to point out. And one more thing is that when we are doing this on an RGB image, we'll be getting an output for the red counterpart, an output for the green counterpart, and an output for a blue counterpart. So what we do is that we'll take these red, green, and blue counterparts, and we'll be adding them together in order to get a output matrix. So this is just simple matrix addition. These are 3 different matrices, and we'll just be adding them together to get the output. So remember, guys, this is only for RGB images. In a grayscale image, we can say that a filter is equal to a kernel because there's only one kernel, right? So there is no group or anything like that. But in the case of RGB images, a filter is a group of kernels. That is 3 kernels that we're going to be using on each red, blue, and green counterparts. So with that important difference out of the way, let's go into some more terminologies of the CNN. So we've looked into convolution. We've looked into what the operation is, and we've looked into a kernel. All right. So I just want to define some more things. You guys would have already seen it, but it has a formal definition. So let's go see what that is. First, we'll be looking at stride. Stride is simple. Stride is basically the amount of steps that we move the kernel every time we convolve. So if you can see here, this is the convolution that we did a few slides back. We took a 5x5 image matrix and we did a convolution with a 3x3 kernel. And just like you can see, we've moved the kernel only one step at a time. So it's only moving one pixel at a time into the right. And that amount of steps that it takes every time we do this convolution is known as stride. So normally in computer vision, we'll be taking a stride of 1 so that we can take every single section of the image. But there are other CNN models that have that take different strides. So if you can look below, I think this animation is a little bit I'll just zoom in just in case. I'll just zoom in for everyone. So as you can see, this convolution is not taking a stride of 1. You see, it's not going to the next pixel. It's going almost 3 pixels to the right. So here it has a stride of 3. So here it has a stride of 3, not a stride of 1. So yeah, a different stride essentially might be taken according to the need of the CNN model. So here we have a stride of 1 and here we have a stride of 3. So stride is just a formal definition. Now the second part that I want to define is known as padding. Now before we go to padding, essentially, I want you guys to think about something. If you remember a few slides back, what I was saying is that when I'm doing the convolution on this image matrix and I'm putting my image matrix on this 3x3 subpart, what I'm doing is that I'm getting the information from this pixel. So this is a pixel that's saying 0, which is in the middle, and where I'm also getting the influence of its neighbors. And we did this convolution, and we were successfully able to get the information from all the pixels that I've put in this white box, right? But one important thing is that we ended up losing in the information from the pixels, information of the pixels which are at the edges. So because look, we can't put this here. I can't put my kernel here because there is nothing here. There will be nothing to convolve. So what do I do in that case? What do I do to get the information from not only the middle pixels but also the edge pixels? And that solution is to pad the image. What we do is we'll be doing padding of the image before we input it for convolution. So if you can see here, it'll be a little bit incomplete, but what padding is essentially is that we'll be adding a layer of zeros around the image. So we had this image right here, and what we're going to do is that we're going to add a layer of zeros. So if you can just follow my pointer, I've added a layer of zeros around this original 5x5 image. So this was a 5x5 image, and I've added a layer of zeros. And now what I can do is that I can take my 3x3 kernel, and now I can actually place it here such that my middle pixel, that is this 3, can actually end up being the middle pixel. So I can now end up getting the information of the edge pixels. So by simply adding this layer of padding around this network, I am successfully able to extract the information of the edge pixels. So when we did this convolution before, if you remember, we only got a 3x3 image matrix, and what that ended up doing was it ended up resulting in the loss of the information from the edge pixels. But now, after doing this padding, we see that it's the same dimension. This is also 5x5. So this image pixel, this is also 5x5. And the output from the convolution is also 5x5. And this is a testimonial to the fact that we've ended up retaining the information from the edge pixels also. So by simply adding this layer of zeros, we have ended up getting the edge information pixels. And also just intuitively, why we're adding zeros is that zeros don't have an effect on the convolution. So everything multiplied by 0 will just cancel itself out, and we'll only be getting the image information from the image specifically. So that's why we do it with a layer of zeros. So that's all, guys. That was padding. And again, another example. This is also another example. We've taken this, we've put our kernel, and this was a 4x4 image matrix essentially. We put a layer of padding, one layer of padding around this image. And when we do the convolution with this kernel, we get a 4x4 image back along with the so the size is the same, and the entire information of the image is that we want to get is retained. All right, congratulations. So that was essentially the basics of what a convolutional layer was. You guys have successfully learned what forms a convolutional layer. So give yourselves a pat on the back. Before we do go move forward to the later parts of this session, I want you guys to just look at this code. But now my friend Ryan will be doing the entire implementation, and it will have the entire code. But let's just look at the convolution code separately. So this is what the convolution code will look like in our PyTorch library. So it'll say nn.con2d. So basically what it means is convolution of a 2D image, and then it'll have 5 parameters. So the 5 parameters are, first it's in channels. What that stands for is number of input channels, and number of input channels is basically depends on the on the colors that we have. So as I told you guys before, if you remember, a grayscale image, that is a black and white image, will only have one channel, right? Because it just depends upon the intensity of white color in that image. However, in the case of a RGB image, we'll be having 3 channels depending on the intensity of red, green, and blue. So the number of in channels here, since we put as 1, will be for a grayscale image. Now, if I wanted to input a RGB image, I'll be putting a 3 here. All right. So that's the in channel spot. Now let's go to the out channels part. Out channels is the number of out channels, and what out channels means is it's not quite similar to what in channels mean. It's basically the number of filters or kernels that we are using. So in the before convolution operation, I simply used one kernel, right? But in real image detection software, we have to use multiple kernels to get multiple features of the images. So we're actually using 32 different kernels to get 32 different features of the image. And the rest of the 3 parameters are quite simple. This is the kernel size that we are specializing. So just as before, since I used a 3x3 image matrix, and here also if I put 3 here, if I put kernel size 3 here, the kernel will be of size 3x3. And again, we have stride and we have padding. There's supposed to be a comma here, guys. So you'll see that in the coding. It's just a small error. But yeah, and we have stride and we have padding. And what stride equals 1 means that we'll be taking only one step at a time. Okay? And padding equals 1 means we'll be adding only one layer of zeros around the image matrix. So yeah, that is the PyTorch code. So this is just a small teaser essentially. And one more thing that I want you guys to see is this formula. So don't be afraid of this. This is like, you don't need to memorize this. You don't need to, you don't need to memorize this, but I just want you guys to see this for your own reference. So what we're doing is we're going to take an input with image and we'll be getting an output, right? And we're doing stuff like we're taking a specific kernel, we're doing a specific stride, and we're doing a specific padding also. So so if you want to just quickly calculate what the output size is, this is the formula. So this is just it is the size of the input size. So if it was like I had 5x5, so it'll be 5 here, and then K will be the kernel size, and then 2 into P, where P will stand for the number of layers of padding that you'll be adding. So if I'm adding 1, P will be 1. If I'm adding 2, P will be 2, and so on. And we're dividing this whole value by S, which is basically stride, the number of steps that we are taking. And we'll be adding the 1. And this formula will work on getting our output size. So you don't need to memorize this, but this is just for your reference. So, all right, so we've successfully looked at the convolutional layer out. So we looked at some more terminologies, right? So we'll be going for another poll right now. So let me just pull that up. Right. So this is the so yeah, we'll be going for the next poll. So do scan this QR again. I'll be giving some time for you guys to scan it. Okay, so I believe there is some doubts from Teams. Let me just go to, okay, so if I go there, all right, people on Teams who have doubts, I will clear it after this poll gets over. So keep your hands raised. I will clear it once this poll gets over. So yeah, so I'm just gonna wait for a minute. I think that's enough time for the to scan the QR code. So I'll be activating the poll, the first question of this poll. Wait, and wait, were you guys? All right. Okay, so. So yeah, you guys can still scan the QR here if you want to join the poll, and I'll be giving you guys some time. We'll be waiting for some more people to answer the poll. So yeah, I think a majority of the people have gotten it. I'll be locking the. Okay, okay, there are still people voting. Let's just wait for them. So yeah, I'll be locking the voting, and let's look at what the correct answer is. And yeah, as a majority of you guys has said, it is 3 cross 3. So for those who've been confused by this question, let's just look at what the question is saying. We have an image of 5 cross 5, and we're applying this convolution with the kernel size of 3 cross 3, right? Now, the tricky part about this question was I asked what is the size of the image without padding. So here it was the original operation that we did. The original operation in which we took a 5 cross 5 image matrix and we put a 3 cross 3 kernel on it. And there we'll end up losing the information from the edge pixels. So it will end up resulting in a 3 cross 3 matrix. So for those who said it was 5 cross 5, I believe that's where you went wrong. You might have thought that it's padding. And 2 cross 2 guys, I believe it. You guys were been confused about the stride or some sort like that. But yeah, this is the correct explanation. This 3 cross 3, it's 3 cross 3 because we're not applying padding. All right, so guys, do stay on this poll. We'll be going to the next question. Correct answer. Right. So I'll be. So I think the voting is unlocked, right? So this is the second question of this thing. Wait, is the poll? Are you guys able to see this? Wait, am I away? No, I've unlocked it. Ryan, is the
Yeah,
question
yeah, I think it's working.
is working, right? Yeah. Okay. So I'll just give some time for people to for it to update essentially. I think there was an updating problem. Oh my god. Okay. Okay. Wait. I think. Okay. Okay. So sorry guys. I think this question is wrong. Is wrong actually. This it has two options which is supposed to be the same thing. So yeah. This. I'm sorry for that. It's. I'll be law. I'll just end the poll right now. I've there's been a small error from my side. Extremely sorry for that. I'll be locking it, and I'll just explain the question for everyone. So because the options are wrong, so there's no point in showing what the correct answer is. So what this question was saying is that we have a 5x5 kernel, just like before, that we're going to be using for convolution. So what should be the padding and the stride that we want so that we capture the entire context of the image? And the correct answer of this was supposed to be wait wait, is it working? No, it okay. So there has been two options with same thing, right? So the correct answer was actually stride 1 and padding 2. So since there has been two options with the same which looked the same, I locked the poll. But so the ones that did get this correct, so kudos to you guys, this was the correct answer. And I'll explain it to you guys, right? So we have a 5x5 a kernel. Now look at this, we have a 5x5 kernel, and if we want to get the entire information using a 5x5 kernel, we have to apply a padding of two layers, not one. Because remember, when we are doing the 3x3 kernel, we added a padding of one layer, and now since the kernel size has increased, we need to add a padding, more padding layer. And also the stride is 1 because, as I said before, if you want to capture the entire context of the image, it's better to put stride 1. So that is the correct answer for this thing. Yeah, so with that, that was the poll, guys. I'll just deactivate this, and and we'll be okay. So before I go there, I think some people have doubts in Teams. I'll be looking at this. Yes. So 1 minute, I'll be unmuting this. So yeah, this Kavita, I think you have a doubt. I think I've allowed you to wait. No, why is it not? Why is it not working? Okay, Ryan, can you help? Can you just?
Yeah, I think Mike is allowed now.
No, I'm trying to allow. Wait. Okay, so Kavita, can you hear me? Yeah, you can speak. You can tell your doubt. I'm sorry, I can't actually hear you. Your voice is a bit muffled. Yeah, I actually can't hear you. So yeah, if there's a doubt, so the chat is disabled, right? No, I'm
If
sorry.
there's a doubt, can you use the Slido link and post it there?
Yes.
Because I think we can't hear you.
Yeah, so we can't hear you, Kavita, but we will. But you can use the Slido link that I showed out, and you can put it there. So I'll be going to the Slido right now since there's been no doubts here. I believe there was another person, but he has lowered his hand, so I'll be going to the Slido link now.
Shabarish, there's one more doubt on Teams. I'm just going to unmute it. You're not audible. Okay, Shabarish, I think you can just answer this question. Currently, your mic is not on.
Okay, so the Slido one. I'll be answering the Slido one right now. Wait, let me try to unmute this guys one more time. Okay, so Teams is not working. I'll answer the Slido one, and if we can figure this out later, we'll allow these guys to unmute at a later time. Okay. So yeah, let's go back to this doubt. So there are basically two different types of kernels, and and if you remember before, I told you guys that there are certain kernels that we use for certain operations, which will be looking right now. We'll be looking at it next up. So those are some specific kernels, and there's something called Gaussian, there's something called Sobel, and those are for specific operations like Gaussian blur, like for edge detection and all that. But in general cases, in the PyTorch code that Ryan will also be showing, what we'll be doing is that we'll take a kernel with some and we'll initialize some random value. So this 3x3 matrix that you guys have seen. Oh, wait. So just a minute, guys. So this 3x3 matrix that you guys have seen right here, this is essentially some random values, and we'll be taking that in the beginning. And what we'll be doing is that we'll do something known as back propagation. And if you've attended the previous classes, what back propagation is that we'll be changing the values of the kernel matrix such that we can get a more accurate output. So it might seem a little bit confusing right now, but this question will make a much more sense. Like the answer that I gave will make much more sense when we go on further. So yeah, I think that's fine. Let's try to do this one more time. All right, so this is in fact not working. All right, guys. So the people on Teams, the two people who have raised their hands, and anyone else who wants to ask a doubt, please do put it on Slido. If you want, I can show that QR code once more in case you missed it. In case you missed it, let's just I'll just show you that QR once more. This is the QR. So if you want, just scan this QR right now. You can go to the Slido page and you can ask your doubt. So I'll just put that on for some 30 seconds. Okay, so I think someone has. Okay, so. So yeah, I think that should be enough. So yeah, let's get on with the presentation. Let's get on with what we've done, with what we. So we've lost. So we left off at this. So we left off at here right now, and we'll be going on to this. Let's just close that and to this. Oh yeah, and guys, if you do want to, yeah, if you just do mark your attendance. This is the QR for attendance. So yeah, this is a thing, and so let's. So I think that also needs some time, right? So we'll be giving some time for that. So it is scannable. It is visible, right? Ryan, it's visible, right?
I think it's slightly cropped. If you exit the presenter view, it should be fine.
Okay, so is it fine right now, or?
Yes.
All right. So guys, do. So we'll just give some 2 minutes for everyone to scan the QR. This is, guys, there will not be any link shared in WhatsApp or in the YouTube chat. So this is the way in which you guys will be able to put in your attendance. So do scan this. Okay, so I think it's fine. It's the QR is scannable, right? Okay. So we'll be giving some more time for this. Yeah. So yeah, guys, I think that should have been enough time to scan the QR. For anyone who has not been able to scan it, don't worry. We will be showing this for 3 more times in this session itself. So yeah, so we'll go on with the presentation. Right. So carrying on with the question that a person has asked of how we can get the kernel matrix. So we'll be looking at the first example that I talked about. Which is some standard kernels that we use to do some specific operations. First thing that I'd like to talk about is something known as Gaussian blur. So now everyone here knows what blurring is. Like what we do is that we'll take an image, and if a blurred part of the image will be something that you can see, you can figure out what the image is. You intuitively know what it is, but there will be a lot of features that have been cut off. Right. So what we do in computer vision is that we do blurring, and blurring is actually helpful for us. So in real life, blurring makes it difficult to look at an image, but in convolutional neural networks, blurring is actually helpful to process the images. So the first thing that we'll be looking at is a Gaussian blur. What Gaussian blur is that? Is basically is a technique that will blur a pixel it'll blur every single pixel of an image. Like I've taken an image of a football here, and it'll give more weight to the middle pixel. So what that means is remember this is just the kernel. This is the Gaussian blurring kernel. And if you can look at all the values here, we've given the most amount of the weight to the middle one, meaning, because remember the middle one is what we care about the most, right? So this is what Gaussian blur does. It will blur the image, but it will give a lot of importance to the middle pixel. So it is similar to the Gaussian curve. So if you guys aren't familiar with it, Gaussian curve is just a probability curve, and it will kind of peak in the middle. It will go something like this. So it is similar to the Gaussian curve. And why do we blur images in computer vision is that it helps us filter out all the noise. And what noise means in images is the unwanted data. So here, so this is a convolutional neural network, and let's say I'm building a model that wants to detect a football. Like I want to just detect this football. So all of this grass here and all that, this is just noise. I don't want that in my image, right? So what I do is that I will wait. Yeah. So what I'll do is that I'll do the Gaussian blur. And by applying this Gaussian blur, what I've been effectively able to do is that I took this original image right here, which has a lot of noise. Look at this, it's all noise. And this stuff will just serve as an obstacle for our image detection. And I've been able to successfully blur it out. It's been completely blurred out. And what you can see here is just the football. And so essentially what blurring of an image does is that it will retain the important information, but it will also got rid of the unnecessary noise. So that's one type of kernel. Another type of a kernel is something known as a Sobel operator. And what Sobel operator does is that it'll get us outputs of just of either vertical edges or horizontal edges. So there are basically two different kernels under the name of Sobel operators. It helps us find these vertical edges and these horizontal edges. So let's look at so let's just look at it in action, right? Let's look at the same image of the football. Now I've taken that image and I've put this vertical Sobel. And as you can see, all this what this kernel essentially has done, what this vertical edges kernel has done is that it has ended up detecting all of the vertical edges. So everything that's going from top to bottom, you can see it's taken into consideration, and everything that's going horizontal, it's not taken into consideration. Only the ones that are going from top to bottom, that's being taken into consideration. And on this side, on this image, we see it's a horizontal Sobel, and this horizontal Sobel ends up finding out everything that's going from side to side. So this is a special type of kernel that we use, and this kernel will get us the vertical edges of the image, and this kernel will get us the horizontal edges of the image. And since the edges are essentially enough to get the input information, we can combine both of these outputs to get our final result. So this is what it will kind of look like. We can take both of this. We'll take this vertical Sobel image. We'll take this horizontal Sobel image. We will do a combination operation, and we will get this. And as you can see, we've now been able to successfully detect all the edges of the image. Is right. And so you can see that the football shape is retained, but with only the minimal information required. So we've reduced the computation time. Now look at the right thing. I explained Gaussian blur, right? This is actually a very good example of why doing Gaussian blur is actually helpful. So in this image right here, what I've done is I've taken the input image and I've put Sobel and I've combined them. And this is what we got here. But as you can see, all this sort of unnecessary noise ended up getting carried on in here. I don't want that. So what I do is that before I do Sobel, I'll do this Gaussian blur. So what essentially I'm doing is I'm taking this image, I'm doing this Gaussian blur, and then I'm applying Sobel. If I do that, I can effectively cancel out all of this noisy data. So there's so much noise right here, and it's effectively gone. And you can see that both the football itself is not affected. There's no distortion here, but we're able to carry out take out all the unnecessary noise. So that, guys, is basically examples of Sobel and Gaussian. There are some specific kernels which will be helpful in doing some specific operation. Right. So this was essentially the full convolution part. Now let's go to the other layers of the convolutional neural network. So we've done with the convolution part. We'll now be going on to the other layers. Now the first thing is something known as normalization. Now normalization is pretty easy to understand. Now you see, if you recall from the first slide, we see that every single pixel value in the image will have intensity ranging from 0 to 255. right? But neural networks will be working better if the inputs are normalized. That is, if the inputs are put in between in 0 to 1. Why we do so? That is what normalization is. We're taking a big range, and we put an operation, and we'll get this, and we'll get a and we'll get this, and we'll basically squeezing this 0 to 255 range into this 0 to 1 range. And why we do this is that it will help reduce the learning time, because the values are now in a much more smaller range, and it will also end up preventing a very important problem that we usually face in machine learning in general, and that's known as overfitting. Now, I think some people who have attended the previous session would be familiar with this, but for those who aren't, I'll just explain what overfitting means. So what are we doing? We're training a model, and we're training a model, and we're training a model with some input images, and what we'll do at the end is we'll put a test image and see how well it's become. But let's say that I'm doing it with this football itself, right? But what the problem of overfitting arises if I put so many similar images of this football. So let's say I take this image of the football, and I put very similar images as such. So this is an Adidas football. Let's say that I put all Adidas footballs, and after this, let's say that I want this convolutional neural network to detect a Nike football or some other brand. It will obviously fail, right? Because it's only been trained on this Adidas football. Also, the phenomena of overfitting happens when a model is only trained to detect a certain type of input, and it will fail in everything else. So what normalization does is that it, mathematically speaking, it will also help in preventing this overfitting of the model. And if we want to look at the PyTorch code of this normalization part, this is what it looks like. It will be shown in the implementations, but it will be something as transforms.normalize 0 and 1. Right. So that was normalization. Again, now next layer. One important thing, guys. Normalization is something that's done to the image before we do convolution. So this is done before the convolution, and then we do normalize. So it's stepwise. It will be normalization, convolution, and then activation. So this is done before, but I just I put it here because we're mainly talking about convolution, right? So yeah, that is normalization. Let's go to activation functions. So just like in the artificial neural networks, which is basically the traditional neural networks, we also use an activation function here also. And what an activation function does is it'll take the range of values that we have in the input image pixels, and it'll change it to a different value depending upon the activation function. So this is a very, very famous function known as ReLU, and it's quite simple actually. What it does is that it will take let's say that I have an image, and after normalization, after convolution, there is an output of the image. Let's say that it's some specific value, and what it does is it will take the maximum of either 0 or x. So if that pixel value was say 4, from this graph, what this function will do is that it will assign the value of 4 itself. So for all, and let's say if it was 2, it will assign the value of 2. But for all the negative values, mathematically speaking, all negative values are lesser than 2, right? So for all of them, if you look at the maximum of 0 and negative, it will be 0. So it'll assign all negative values as zeros. So what it's actually doing is it's eliminating all the negative values from the convolved image pixel by converting them into zeros. So, and this is how the function essentially looks like. The code essentially looks like it's nn.ReLUof. So that was the PyTorch code of activation. So guys, we've gone through normalization, we did convolution, and now we did this activation also. Right. So the final part of a CNN network essentially is something known as pooling. Right. So let's go. So before we dive into pooling, let's look at the first problem that we had. In traditional neural networks, what the problem that we had was the input was simply too large, right? So it was just too large for the computer to process in a reasonable time, and also the translation part. And we've solved but we have solved the translation part by doing the convolution. We've ended up getting the features by doing the convolution with the kernels. However, there's still the problem of dimension still persists, because if you remember, if I put a padding for the image and I do the convolution part, the size of the image matrix and the size of the output matrix are same. They're exactly the same. So we haven't changed the dimensionality, we haven't reduced it, and for that we need to do pooling. So what pooling is that we end up reducing the dimensionality of the convolved image. So normally a stride of the size of the block is used, so there is no overlap. And the reason that we do this is that the main thing is that we want to reduce the size of the image. And over many tests, we also found that pooling has removed unnecessary detail, and it has ended up resulting in preventing the overfitting part. So this will make sense. So let's just look at the two types of pooling. So to see what I'm actually talking about. So there are two types. There's one known as max pooling and one known as average pooling. These two types are the ones that have been used most frequently across CNNs. So let's look at them. So what is max pooling? So we have this. Let's leave that this is the feature map, or what a feature map is basically the output from the normalization, convolution, activation, from the convolution part. Right. So we got this, and what are we gonna do with this, right? So what we want to do is that we want to reduce this dimensionality, and what we do is we usually take a 2x2 filter. So we take a 2x2 matrix. So we divide the entire convolved output that we got from the activation function, and we divide this into all these different types of subparts. And what max pooling does is that it reduces our dimensionality by taking only the maximum value of each subpart of the kernel. So if you can see in this red subpart, the maximum value is 4. So we'll be taking 4. Here it is 7. So we'll be taking 7. Here it's 8. So we'll be taking 8. And in this part it's 6. So we'll be taking 6. So what we've done with max pooling is that we've taken out the most prominent features of the image. It's because, as you can see, if it's 4, then it's more prominent. It has more intensity. Here it's 8, so it has more intensity. So the most prominent feature would be some shape like this, or of this sort. And we've been able to successfully get that part of the image and also reduce the dimensionality. So what max pooling does is, by getting the maximum element from each subpart, we'll be able to get a feature that is most prominent while also reducing the dimensionality. So this 4x4 image matrix has basically been halved. It's now been 2x2. Let's go to the next type of pooling, that is average pooling. So average pooling is the same thing. We take this image matrix, take a 4x4 matrix, and we do this and we divide it into this 2x2 subparts. But the mathematical operation is a bit different. Here, instead of taking the maximum value, we'll be taking the average of the values. So here, the average of this, if you guys will calculate it, will be 124. And similarly, in this pink pixel, all of these values divided by 4 will be 95. So 8 plus, and here yellow, 8 plus 4 plus 125 plus 59, it will result in 49. So this is known as average pooling. And intuitively what it does is that in some certain CNN models, we don't only want to get the prominent features. We want to kind of get all the features. So what we do is that we'll be taking an average so that we will not be ending up missing any features. So those are the two different types of pooling: max pooling and average pooling. Both of them have successfully reduced the dimensionality of our image. But in both of these cases, but the type of pooling depends on the person who's building the model. Okay? So one who is using max pooling wants to take the most prominent features, and one who wants to do average pooling wants to probably take all the features but also wants to reduce the dimension, so he will be taking an average pool. Again, this is another example of pooling. I've taken the same matrix X here and I've done max pooling on this side and average pooling on this side. So you guys can just look at it again. So if it's so the maximum part here will be 165, maximum part here will be 88, and so on for the max pooling part. And on this side, average pooling will be taking the average of the values. So right guys, that was pooling. So what is pooling result in? So now we've basically crossed through all the different types of convolution. We've started from normalization. We'll do normalization, we'll do the convolution that we talked about, and we'll do the activation, and we'll do the pooling. So these 4 layers essentially will end up resulting in this output. And now that the dimensions of the image have reduced while retaining the features, we'll now be putting this outputs into a neural networks. So instead of traditionally just putting the image data into the neural network, we'll be putting the output from the pooling layer into the neural networks. And what this process is called flattening. So it's just a fancy term. We'll just be taking all these outputs and we'll just be putting them into every single node of the neural network at the end. And at the end, what we'll be having is a fully connected neural network. And finally, we will input our results into the neural network to run the classification. So let's just recap over what we've done. We've done the convolution part, but the convolution has successfully helped us learn the features of the images. Then we've also done the activation. Then we first do normalization, right? So we'll do normalization, then we'll do convolution part to learn the features of the image, like first features of the image, and then we have done activation. We have gotten it all positive values, and finally we have done pooling. So taking the image and reducing its dimensionality while retaining its features. So after doing this, we'll be adding all the outputs, all the numerical values that we got from the pooling layer into this fully connected neural network. So this is the final step of a CNN model. And to visualize this better, I'll just show you guys the entire network. So this is what a traditional CNN looks like. So let's go over it. There's an input. We have an input of a zebra in this case. We'll be taking this. We'll be doing convolution, and then activation, then pooling. Now and in this session, I've only talked about one convolution, one ReLU, and one pooling. But in reality, images are much more complex, right? So they'll be of much higher dimensions and having much more features. So we need to have multiple layers of such. So we'll be doing convolution, ReLU, and pooling multiple times. So here we're doing it 3 times. And as you can see, we've got the final output here from the final pooling. And this is what flattening is. We got these outputs, and we'll just directly putting them as a vertical array just for you guys to imagine it, and we'll just be feeding those outputs into the neural network. And this, my friends, is the traditional neural network that we all know. This is the neural network that we talked about in the previous session. But now this neural network has much lesser input, and it can easily compute this in a much faster time. And as you can see, we're successfully able to get out the probability distribution of what this is. So it has been able to carry out the classification using the features of the image. So yeah, that is, my friends, is the entire CNN network. We've gone through the entire part. So yeah, congratulations, you guys have learned it. There is one more small thing that I'll cover after that I'll be taking up doubts. So if you guys do have doubts, just wait and yeah. And that small thing is something known as back propagation. So just a small recap, what back propagation is that if you look at this output that we got here, we've got an output that zebra is 0.5 7, right? But let's say that this is not good enough. Let's say that I want a more accurate model. So what would I do? I will be training my model. I'll be updating the parameters in this model, like the weights and biases, such that it'll give me a better output. So that is what back propagation is. So that is a simple definition of back propagation. And we have to do this. And in this case of CNNs, essentially, we have to do back propagation not only for this not only for this neural network, but also for the kernels that we're using here. So if we go back to the question that someone had asked in the Slido, they asked how do we get the kernel matrix, right? So we talked about the example like Sobel and Gaussian where we had the custom ones. But let's say that in other cases, what we do is that we'll take a random kernel and we'll be training that kernel. Such that and we'll be updating its kernel values such that such that this probability at the end will increase. So let's see how we actually do that. So this is going to be a slightly mathematical, but I'm pretty sure it's going to be understandable. So yeah, just look at this slide. So let's just look at this very simple image matrix again. So we have this 4x4 image matrix, and then we have this kernel, which is outputted this. But let's say that this output right here is kind of far from what we actually want. Let's say that we want another output. We want to target something else. So mathematically, how we will do that is that we need what do we need to do? We need to update this value of W1. We need to update every single value, but let's just look at this value of the kernel first. So what we'll be doing is that we'll be updating this value using this mathematical operation. So we'll be taking I'll just say what these things are. The x1, x11, x22, and so on are from the image. So these were x11, x12, x21, x22. These are from the image matrix. So x11 here will be 50, x12 will be first row, second column, 125, so on and so forth. y11, y12, y21, and y22 are the results that we got. So y11 will be 83, y12 will be 179, and so on. And t11, T12, T21, and T22 are the targets. That we actually want the kernel to detect. We don't want this. We want another matrix. So this is the derivative of the loss function with respect to this kernel value. And if we were to add this in a similar way that we do for neural networks, we can successfully update the weight right here so that it can detect the target values. So that's all, guys. That's back propagation. So I believe that would have given a pretty intuitive notion of what back propagation in CNN is. So like just to recap, we don't only update the weights and biases of this network. We'll also be updating the weights and the values of the kernels also. So yeah, that was the entire CNN network along with back propagation. Yeah, I'll be giving you guys some time to scan this QR. Let me just escape it. Yeah, so this is the QR code, guys, for the attendance. Do scan it. This will. Yeah, so Ryan, it's completely visible, right? We can see this QR code, right?
Yes.
Okay, fine. So I'll just give everyone some 2 or 3 minutes to scan the QR code. And okay, so are there any doubts in Teams?
No one's raised their hands.
Okay. Then, all right. Yeah, so if you guys don't feel comfortable in actually speaking out, you guys can ask your doubts in the Slido. I'll show that QR again if you guys want in the after this attendance part. First, yeah, but let's just focus on this attendance. And yeah, it will be actually pretty nice if you guys do interact with us and ask your doubts, because I have conducted the session, but since it is online, I'd like to know what doubts you guys have. So do do use the Slido. Do use it to ask any doubts that you might have, because it'll be helpful not only for you guys to learn this thing in a better fashion, it'll also help others. So yeah, do send your doubts, and or if you have any doubts, just ask in Teams also. Okay, the Teams is not working, right? So do use the Slido part. So after the attendance, I will show the QR again. So if you have any doubts, do keep them prepared. I will show the QR for the QR for showing the QR for asking doubts. So I
There's one doubt on Teams. I'm going to try unmuting them again and see if it works this time.
sure, do try that. I'm not sure why it's not working. It's can it if Sumed is online, can you ask him to try doing that? Or I'm not sure if it's a Teams.
Kavita, it's not audible. Can you ask it out on Slido?
Yeah, I think they're not able to talk, but try unmuting. I think there's another person, right? There's oh, okay, no, I think they've lowered their hand. Right. So guys, that I think that's enough time for attendance. So even if you weren't able to scan or something, we will be showing it two more times again in this session. But do keep your phones ready to scan the QR. It can be scanned, or at least take a photo of it when we're taking when we're showing it. But yeah, it will be shown later. Yeah. So this is. So let's go. Yeah, so this is the attendance part. Let's go. Yeah, and I'll just show. And this is the Q&A QR, guys. QR code, guys. So as I said, if you have any doubt at all, you don't need to hesitate in asking any doubt. If you can just scan this QR code and ask it anonymously, and I will reply in Slido. So do use this feature. I'll give you guys a minute or two to scan this and ask any doubts. Ryan, is it possible to allow like unmute everyone at once just for this session? Also, guys, this is we can, I think, okay, so just for now, is it possible to unmute everyone so that if people aren't able to raise their hands or something, they can still unmute and directly ask their doubts?
I was able to unmute the person who raised hands, but
yeah, sure, but like,
and they turned on the mic, but nothing was audible.
Okay. But let's just let's see if you can unmute everyone, like give mic access to everyone just for some time. We'll see if it works. If it's
Okay,
anyone wants to. And I think we can also go for we'll take the shall we take the doubts and go for a break, or shall we go for a break now itself?
I think we'll take the doubts first.
Right. So yeah, I think you guys will be scanning. Let's just see if there's any doubts. Okay, nice. There are some doubts that have been popping up. There have been 7 questions. So guys, do wait in Slido. I think people have started using it. I'll just give everyone else some more time to scan the QR and keep it ready. And if possible, do keep it ready for the entire session. I will, like my friend Ryan will also be taking the code part, right? So there might be some doubts in the code part. So if so you can ask the Q&A through the for the code part, for the implementation part through that also. So yeah, let's just wait for one more minute for anyone else who wants to put their doubts through Slido. Okay, so I will now take the doubts that have been coming in Slido. Right, so we saw this doubt, how we can get a kernel matrix. I think there is an anonymous doubt. Keyboard entry, read network, and link. I think someone has. So sorry guys, I can't understand what this means. So if you were the person who did put doubt, please put it in a more understandable fashion. I can't understand this. Yeah, okay. So someone has asked me, what can you explain black propagation again, please? Okay, so right. So we'll go back. We'll go back to the back propagation part. So what back propagation is on an intuitive scale is that, as I told before, this network right here that I've trained here once. What it's doing is that it's saying that the image that I have is 70% a zebra, but it's also having something like, it's saying that it could be 20% a horse or 10% a dog. But I don't want this. I want my model to say that it's say more confidently that it's a zebra. I want something like an 80% or a 90%. So what I will do is that in all machine learning, what we'll do is that the problem arises with the parameters of this model. So every single neural net, so these are the neural networks, right? And all these neural and all the layers will have their own weights and biases. And this weights and biases and what we have to do is that now we have to change these weights and biases such that we will increase the probability distribution of this thing saying that it's a zebra. Now that's in a traditional neural network. In a traditional neural network, you'll only have this part. You'll only have this fully connected layer, and you'll only update the weights and biases. However, in convolutional neural networks, what we have to do is that we also have to update the kernels, because remember, these features affect the output. So basically we have to figure out a better way to get the features, and that is why we change the kernel value. So if you can see here, if I've explained here, is that this was this traditional convolution that I did, right? So let me just take something. Let's just take this. So this was a traditional convolution that I did, and let's say that I have to change every single kernel now such that the probability distribution of it saying that it's a zebra will increase. So this was my result. But let's say that there is but the target is that I'm just going to draw this out for you guys. I think it wasn't clear in the first. Okay, just give me 2 minutes. I'll just draw it in a bit more bit better. So right, this was the original thing that we got from the convolution. Now let's say that let's say that if we want a better probability of this part saying that it's a zebra, we want it to we would want something else. We want it to go to some other value, and that value we can say it's something like targets, and that's what we define as targets. We'll say that's T11. Sorry guys, it's actually a little bit difficult to draw. I should have probably yeah. So it's called something known as T11, and here there will be something known as T21. Right. So these are the targets. This is probably some of the numerical value, and this is what we want this 83 to be. We don't want it to be 83. We want this to be T11 or T21. And so how do we do that? How do we get to T11 or T21? What we have to do is that we have to change the kernel. We have to change this value. And how we'll do that is that so this new value of this weight of this W that we getting W11 would be of this W11 would be something, would be basically the W11 would be basically equal to the W11 that we already had. So we'll call this W11 star. I think everyone can see what I'm writing, right? W11 star. I think it's minus of alpha into alpha is the learning rate. So this is something that you guys will be putting into the change in the loss function by the derivative with respect to this weight. So here, this is the learning rate. I think you guys would have learned about learning rate in before sessions. It's just the rate at which we change the weights in the new thing. So this is how we will be getting a new value of weight. We'll take this value, we'll be multiplying it by an alpha, and we'll be using this to update this weight. And this weight essentially will change this. It'll not be 1 anymore. It'll be something else. It'll be W11 star, and thus that essentially will give us a better probability of it predicting that it's a zebra. So that is essentially what back propagation is. Yeah, there's another question. Should we ever form specific kernels for any specific task, or should we generally use general ones? So it depends on what you want to do. So yeah, if you want to do a specific task, if you want to detect edges, detect horizontal edges, detect vertical edges, etc., we'll be using those specific special operators like I talked about, like the Gaussian one and the Sobel one and so on. But in general, let's say that you're just training the model and you're just training the model. In those cases, we'll just be specifying the kernel size in the code and using any random kernel, and its values will be updated by back propagation. Can you explain how we get DL by DW formula in this for a neural network? Okay, so the DL by DW, okay, I did forget to mention this. This is essentially what we get from MSE. This is mean squared error. So the error will be something like y. Let's say that the error. So this is 83, right? So this is 83, and we wanted to go to target 311, and the error would be something like 83 minus T11. And we will take MSE is basically this square, and this square, right? So however, if we were to actually 83 will not be represented as actually 83, it will be represented something like Y11. And if you were to take a derivative of the Y11, if you were to take the derivative of this function, you'll end up getting this value, this beginning part. And if you were to do that for every single Y11, for 83, for 179, for 338, for 80, you'll get this entire thing. So that's the L by D. Yeah. So there's one thing. Can you explain how kernels help in extracting the features? I'm still confused. Okay. So let's look at it. So no need to get confused. Let's just look at this example that we saw here. So yeah, this was a specific kernel. This was some specific mathematical value that a person had created, and what he did and what we'll be doing is that let's say that we take this specific kernel. So I want the person to remember this kernel, and what we did here, if you guys can recollect, or I actually did not mention Sobel before, but let's say that I took this Sobel, it's the same thing as you can see. It's the vertical edge detection part, and I put it here. You can see what I'm doing is that I'm doing convolution with this Sobel part, and in an image wise, just as an image, you can see that if I do the vertical Sobel, I'll be able to get these vertical edges. I'll be able to get all these vertical edges. Now, another way to think of it is that if you can look at this matrix itself, it's giving 0 values for everything in the middle, right? So it's not, so basically if there's something going horizontal, it will not detect it because there's a 0 in the middle. It'll only be able to detect this vertical edges. It's just going all straight from top to bottom. We just think of the same thing as in the horizontal edges also. We can't detect anything horizontally with this accurately because it has a zero in between, but we can surely detect everything that's vertical because everything that's sorry, we can't detect anything that's vertical, but we can detect anything that's horizontal. And let's look at the image again. I think this should be a good explanation. We got the vertical edges and we got the horizontal edges by using those specific kernels. So yeah, there's some more. Sir, padding will only take the maximum value for each matrix. Then why are the remaining value? Then why remaining values are left? Remaining values are actually not left. They will not be considered. So if you want to go to max pooling part and we looked at this specific red matrix, we'll take 4 and we'll put 4. Then we'll be ignoring all these 3, 1 and 2. They'll not be used. They'll be ignored. They'll not be coming to the next layer. So that's one thing. And okay, then will the prediction be correct? I think this was part of another question that someone wanted to ask. But it's not the complete question, so sorry, I can't answer that. How does a neural network know when to backpropagate? Okay, so the neural, so in this is a common fact that will apply to all machine learning. We'll be doing backpropagation after every single iteration. So what we'll do is that we'll take this. So in this case, we'll take this zebra image, we'll put it through, we'll get a probability, and as soon as we get the probability, we'll do backpropagation. So it's not something that we activate on our own or something that we something that the model does after a specific period of time. It's almost instantaneous and it runs through a specific number of times. The more accurate definition will be something known as an epoch, but yeah, it will run through an iteration is called an epoch. So it will run through many epochs and to do the backpropagation. And finally, we have this question: will there be any loss of information in average pooling, and won't it affect the accuracy of the model? No, actually, there isn't a loss of information accurate in average pooling. You see, average pooling and max pooling are used in different cases. They're not going to be used in the same cases. In max pooling, you wanted to get the prominent features, but in average pooling, we're not losing any features. We're taking the average of the values, right? So if it this, so you can see, let's say that this is a RGB image, and by convention, this will have a higher intensity, and this will have a lower intensity. But as you can see, this is the average of these values will go to something in the middle, which is a grayscale. So we've successfully have captured the features. So it won't actually result in any loss of accuracy. So yeah, I think those are the questions from the Q&A. Yeah, so I believe that so that is me. That was me. That was Abhirish. We will now be going for the break, guys. We'll be going for a break of I think of 5 to 5 minutes, and then my friend Ryan will take over. So guys, so yeah, this is. So yeah, this is the break. So yeah, will be I think we'll be starting at somewhere around 7:03 or 7:04 ish. So yes, yeah, and I have put the Q&A QR code again on the screen. You guys can still ask. You guys can still scan it. And this will also be important for the next session because the next session is showing just a collab notebook, right? So if you guys have any doubts, do keep the QR code scanned and ready. Okay, guys. So I think the break was sufficient. I hope everyone has scanned the QR code. This Q&A QR code. This will be extremely important for you guys to ask doubts to Ryan when he's implementing the when he's showing the implementation. So do scan this. I'll just give some 30 seconds for you guys to scan. I've showed this for a long time. Just one, and then Ryan will take over.
Shabarish, if possible, can you even show the attendance QR right now?
Okay, sure. Yeah, this is the attendance QR.
Yeah, because there are many people who are requesting to show it again. So the people who weren't able to scan earlier, please scan it right now. We'll be giving you another 30-35 seconds. And also the people on YouTube who are watching the session on YouTube, if you can message on the groups if you are able to see the screen, because I guess earlier when we were showing a static screen, generally it was going blank. And also the people on MS Teams, if you have scanned it already, I guess it'll be helpful for us if you react with a thumbs up or with any other emoji. All right. Okay. We'll wait for another 10-15 seconds and then Ryan can begin.
Okay, guys. So I think that was enough time to show the QR code for attendance. Ryan will again show it to you. So don't worry. So yeah, that's me. That's me, Sabrish. So yeah,
Okay, good evening, guys. I'm going to be taking the session for the implementation part. Okay, can you react if my screen is visible, please?
no, Ryan. I think we're just seeing a black screen. Okay, let's give it some 5 seconds.
If you're facing any trouble, probably you can even consider leaving and rejoining the meet. That helps.
Yeah, we can't see your screen, Ryan. Can you try that?
Fine.
Okay, yeah. Now it works.
Oh, okay.
Okay,
reshare
right.
it again then.
It worked. It worked.
Okay. Okay. Is it visible now?
Yeah, and Ryan, click on F11, make it full screen, and
Yes.
also zoom in a little.
Okay, so as of now, I'm just showing a from scratch implementation of convolutions alone. I have not implemented a neural network because that'll be really quite complicated. As you can see, even just doing the convolution on an image already requires this much code. I'm not going to go into detail on this because this is all very simple in PyTorch. This is just code for reading and writing the image. In case you are wondering how we combine the vertical and horizontal Sobel operators, we basically took the square of the vertical image and the horizontal image and then took the square root after adding the two.
Ryan, sorry, can you just zoom in a little bit more so people can't see?
Okay. So this is the convolution, and I'm not going to go into detail on this.
I don't think it's updating, Ryan. I think we're still in the same think. Can you try again? Can you try zooming in again? Right. Yeah. Now it works.
Okay.
Now it works. So yeah, you can go back to the top.
Right. So anyway, as I was saying, please don't worry about the code here. But this is actually an implementation of the convolution. And actually, if we go to PyTorch, all of the convolution layers can be finished in less code than this. So here, as you can see, the code is working and you are getting the operations on this football. I also wanted to mention that the normalization step can be done like this. Shabri showed the transforms to normalize. That's what I'll be using in the main code. But if you have it in the form of NumPy arrays, then you can actually just divide by 255 because your values are in between 0 and 255. Now I'm going to actually move on to the neural network. So I'm going to be using the fashion MNIST dataset for this. It's a dataset of clothes, basically, and our neural network has to identify the type of clothes. These are the clothes in the dataset. Our network will be outputting integers, and those will correspond to the indices of this array. Now, these are some examples of the images in the dataset and the target values. Hopefully, our model will, at the end of this, be able to correctly guess most of these. Now, this is the transformations. We often use this. As you can see, it's imported from Torch Vision. We'll often use this when we're getting a data set from, again, Torch Vision, so that we can easily shape the image correctly, turn it into a tensor, and normalize it. This code lets us download the data set only the first time. Afterwards, it'll just use whatever's downloaded. Otherwise, you'll have to spend a lot of time getting it from the internet. So now I'm going to come to the network. Now, this is the convolutions part of the network. So as you can see, first we have this function nn.conv2d. Now, in channels is 1. Now, we have 1 channel because these are all grayscale images. If we had a colored image, then we have to have 3 channels, red, green, and blue. And out channels 32. That is, we want our model to learn 32 features in this step. Now, a kernel size of 3. Here I can actually also use 3,3. That's also fine. And in case I want to make the kernel a bit different, I can use this kind of kernel. But if it's square, then I can just write 3. And stride is 1. I don't have to include this in the arguments for the function. This is the default value. Padding I do have to include if I want to make it 1, because it'll be the default will be 0. So after this, I've done standard activation function. This is what you'll use in normal artificial neural networks as well. And next one, pooling layer. This will use 2 cross 2 blocks. As in the case of, I can do something like this as well, as in the case of the convolutions, but there's no need for that really, at least for this model. Now afterwards, once we made 64 features and done pooling twice, now we have to put it into a regular neural network, because at the end of the day, we still need to predict which type of dress it is. So first we'll use nn.flatten. This will basically turn our image into a straight array, a flat array. And the size of this is 28 into 28, because that was the size of the image. Then into 64, because we have 64 features. And then divided by 16. That's divided by 4 with this because this is a 2 cross 2 block, and then 4 again. So divided by 16. And now we're going to have our first hidden layer of length 600 and our second hidden layer of length 128. Finally, we have 10 output neurons, one for each class. So the forward function is like this. Because this is an nn.sequential, we can just write x is equal to self.convolutions of inputs. And it will run all of these convolutions on the network. And then we do for the fully connected network as well. I also defined an artificial neural network so we can compare the accuracy. Here, as you can see, this is just the fully connected network with some more activation functions. And the optimizer I'll be using for this is add-on and the cross entropy loss. Now, this is the training function. The training function is pretty much the same as your normal neural network. This is why we use PyTorch. It deals with a lot of stuff for us. So this is the forward pass. This is the entire forward pass. And as you can see, in every single forward pass, for every single forward pass we do, we'll also compute the loss and perform the backward pass. These two will perform the backward pass. Optimizer.step will change the weights, and loss.val.backward will give the gradients. This function is there to ensure that the gradients aren't simply added. So this is our evaluation of the model. There's a separate function to do this at the end, but I'm just doing this here so we can see the accuracy over time. And as you can see, the accuracy increases quite rapidly and then lands up around here, around 90%. These red lines are just so you can easily see how good our accuracy is. And this is how I've trained the CNN model. By the way, I'm using mini batch gradient descent and only one epoch because we have enough mini batches. And in any case, we're getting around a 90% accuracy. Now, then I've repeated this for ANNs, and the situation is not so good here. As you can see, ANN's accuracy is around 50 to 60%, significantly less. This is the accuracy of the entire model. As you can see, CNNs are nearly 90%, ANNs barely crossing 50%. And this is basically the reason why we use CNNs over regular artificial neural networks. This I just used to explain what some of the functions do. Now, I'll come back in more detail about the functions, but I hope you guys have understood this CNN class. So I'm going to ask a question about this. Okay, so I'll give you guys about a minute to scan this QR code. Okay, I'm going to try and activate the poll. Is the link working? Shabarish?
Yeah. The link is working. I am able to get the question, and yeah, I'm able to also answer.
Okay, fine.
You,
That's good. So be careful. I've tried to answer this in a tricky way. Don't worry about these exact values. You should be able to get this just by using an approximation. You should be able to understand what I'm trying to go for. There's a mistake in the spacing here. There should be a comma. Sorry about that. Okay, guys, answer quickly. I'm going to close it soon. In case you're forgetting what the values are, the first value is in channels, then out channels, then kernel size, and then the other ones I've specified is necessary. Okay, I'm going to lock the voting now. Okay, so most of you have got the correct answer, but there is some confusion. So I'll try and explain. So firstly, this is an RGB image. So that means we actually have 3 input channels, not 1. So that's why the second option is wrong. Now,
Ryan, just a small interruption. Can you just show the? Can you just click on the play button so they'll see the correct answer?
I think the correct answer is visible. It might be lagging a bit.
Okay. So we'll wait. We'll wait.
Is it visible now?
No, it's not actually updating, so that's why I wanted to. Can you maybe switch tabs and come back?
Yeah.
Maybe. See if there's.
Okay, in any case, guys, the first option is correct. In case you can't see that. Most of you have voted for that, so that's good. As the first option shown on my screen. nn.conf2d of 3, 30, 3, 3, stride equals to padding equals 1. So now firstly, this syntax I've used. Now I can also put 3. That's still correct. Both 3 and 3, 3 are fine. For this, both will use a 3 cross 3 kernel. Now, because we're reducing the image size to 64 by 64, that's why our stride is 2. Now, padding equals 1, that you'll get by using the formula, but I've try to make sure that doesn't matter very much. So this stride equals to will basically reduce the image size by about half, because now you're taking only about half as many convolutions. Shabarish, are you able to see now?
Yeah, it is updated now. It is updated now.
Okay. Yes, I am showing the Slido at the moment. So basically using the stride equals to, we're able to change the size from 127 by 127 to 64 by 64. Okay. Now I'm going to move on to the next poll. So now this poll is about, guys, please scan the QR code. This poll is about nn.maxpool2d. So nn.maxpool2d is supposed to do the pooling for us. I'm using max pooling here. The same answer would really apply to average pooling. I'll wait for another minute or so to let everyone complete. Okay, I'm going to lock the voting now. Yes, as most of you have answered correctly, I think it's clear that you should use maxpool 3 to the of 3. So the reason this works is because when you're using 3, then you're using a 3 by 3 block. So then if you have an image like this, you will first do the lagging. Basically, it will split your image into, it'll take the first 3 rows and 3 columns, make that one thing. Next, the next 3 rows and then columns 4 to 6, and turn that into 1 pixel. And then once you're done with all that, it will be divided by 3 for the number of rows and 3 for the number of columns, so totally 9. Now, nn.maxpool2d2 is wrong because that'll actually reduce the size of the image by 4 times. So that's why we wouldn't use that. nn.maxpool2d of 9 would reduce it actually by 81 times, which is probably a bit too much for a lot of images. But still, if you have a very high resolution, that might be useful. Okay. Does anyone have any doubts right now? Okay, in that case, I'll share. I think I'll share the attendance. I'll come back to. Is the QR code visible? Shabarish?
Yes, yes, it is visible. Let me just try scanning it. Actually, Ryan, can you just zoom out on Canva a little bit so that it's visible? It's
Okay.
yeah. Just use the thing, the bottom. So we just it'll be helpful for everyone. But it is scannable. Do yeah, it's scannable. I think it should be pretty much fine.
Okay, I'll come back to more details about the implementation after this, and I'll try and explain some more of the details about the rest of the network. Does anyone have any doubts with the CNN's part specifically? How I've defined the network in the CNN class. Okay, guys, the main part of this session is over, which is explaining how CNNs work. So if you've understood that, then that's good. Our previous sessions have also explained in more detail about how regular artificial neural networks work. But I'm still going to try and explain some of the code here. So here, this is forming a data loader. This is basically splitting our data into mini batches so that we can do mini batch gradient descent. So every bit of data that we put into the model will have a size of 128. For both the train and the test data set. This is just visualization. I'm not going to discuss that. Then this part I have discussed. Again, if you have any doubts, please don't hesitate to ask. The optimizer, Adam, is basically a better version of ordinary gradient descent. It involves both momentum and some of the aspects of RMS propagation, which involves changing your learning rate. This is the training loop. Now here, this is the forward pass. Forward pass is just one line. Now for the backward pass, and this is done for every neural network, we first have to calculate the loss. Now again, the loss is also a built-in function, nm dot cross entropy loss. Now this line is important because otherwise it will keep on adding the gradients rather than resetting the gradients after each step. Now after this line, we'll do the backward pass with the loss value and we'll calculate the gradients and then use optimizer dot step. This will adjust the weights. Now, some of these functions you might not be familiar with. This is basically a way to pick the maximum probability of our prediction. So our prediction is going to have an output size of 10. as you can see here. And that's going to be outputted in terms of probabilities. So the highest probability, that's why we have max, is what's going to be our predicted value. So this will basically return the classes as numbers. This syntax will basically return a true or false array. That's this one basically. So as you can see, most of the values are true. And then it'll add all the true values here into the correct values. And the accuracy will be correct by length of targets. So here it's just 128, and we're just checking the accuracy for various different mini batches. And then this is just plotting the graph. The same thing is done for the artificial neural network, except that here we're not using any convolutions or anything, but we're using the same train loop. And the only the only thing we're changing is the optimizer and the model. Here we're training the CNN model with the CNN optimizer. Here we're training the ANN model with the ANN optimizer, because we have to pass the parameters of the model here. That's why we can't use the same optimizer for both. They'll have different weights. This is the accuracy function. This is basically doing the same thing as it did in the train loop, except that it's iterating over all mini batches. And that's how we're getting the total accuracy. So as you can see, the accuracy with the CNN is really high and the accuracy with the ANN is quite low. Okay, now, if you want to leave, I think you can leave now. If you have any doubts, please don't hesitate to ask them. Ask them on Teams or on the QR code. Please raise your hands if you have any doubts.
Ryan, maybe you can show the QR, right? You can show the QR.
Oh yeah, sorry. Is it visible now?
Yeah, the QR, Q&A QR is visible, so they can ask their doubts.
If you have doubts in any part of the implementation, you can ask now. Do you want me to repeat any part? Okay, I've allowed the mic for you. Can you try speaking, Krishna? Any other doubts?
I don't think we can unmute the person. So Krishna,
I think he's showing up as unmuted, but he's not. If you're having any difficulties unmuting, please also ask on the Slido.
yeah, do ask on the Slido, guys.
Okay, Shabarish, are you hearing me?
Yes.
Okay, fine. Can you elaborate about kernel values, the matrix values? I see 1, 0, -1, something. So
Yes.
how that was determined?
Okay, so specifically those values you want to know.
Yeah.
Right. So those are the Sobel operators. Now, so I think I'll just show it in the PPT. Right. So as you can see here, this is, if this one has a very high value and this one has a very low value, say if all of these are 255 and all of these are 0, all of the values here, we're ignoring the values in the center for now, then what you have essentially here is a white line. This part is white and this part is black. So then this is what we'd call an edge. And that's why this operator works. Of course, we have a horizontal thing, horizontal edge, then this part may be 255, this part may be 0, and it's not going to work. That's why we have vertical and horizontal operators. And also we care more about something that's closer to the middle kernel. That's why this has a value of 2, whereas this only has a value of 1. So this will actually detect the edges in a neural network like that. That's if you want the qualitative thing. In general, we don't really need to do most of this because PyTorch will randomly initialize kernels and do the backpropagation to find the best kernels for whatever our model is doing. But this is specifically more useful in edge detection.
Okay.
Is that clear now?
Yeah. Thanks, sir.
Any other doubts? Do you want me to explain anything in any more detail?
Yeah, Ryan, one more question.
Yes.
What is the maximum kernel size? For small image, we say 3×3. For bigger images, what can be the maximum size?
technically you don't need to have a maximum size. That is, any kernel that's shorter than the image will work. And if you allow for as much padding as you like, then you can take any kernel. But usually 3x3 is a good size. We prefer small kernels because if you have big kernels, then that's actually quite similar to an artificial neural network. And that's not as useful.
Okay.
Small kernels are better for capturing more local information.
Okay, right. Yeah, thanks.
Guys, if you have no doubts, you can leave.
Ryan, yeah, I think there aren't any more doubts. I'll just check Slido. Yeah, so there aren't any more doubts. I think we can end it. Ryan, am I audible?
Yeah. Yeah, I think
Okay,
we'll
yes.
end it.
We'll end the session. So
We'll end the session.
thanks everyone. Thank you everyone for coming.
Thanks for attending. Please do attend our next session as well.
Yeah, the next session will be building upon the CNN topic. Another two coordinators they'll be speaking of some more CNN models. So it'll be quite interesting. So do it in the next session. It's going to be on Monday. And yeah, with that, I think we can end.
Also remember,